Alright guys, now that my Clever is working properly, let's go back to talking about mapping Earth. So when was the last time you used a map to find information? Maybe you looked at a map of your school to find your classrooms, or maybe you reviewed the map of the school to practice for a fire drill or a disaster drill. A map might show all of the exits or the safest rooms to go if there were a tornado. There are many kinds of maps, such as road maps, trail maps, and weather maps. Each type of map contains different information and serves a different purpose. A map is a model of Earth. In order to remodel Earth's surface, you can make flat representations of an area on Earth on a piece of paper. So in order to model the entire planet and its shape, you make a globe. Most maps are drawn in map view. They're drawn as if you were looking down on an area from above. So map view can also be referred to as plan view, and it's shown right here. Okay, so here's plan view. So this is a house, and we're looking at the inside of the house as if the roof were off and we were looking down from inside. Okay. Map views and profile views will be used to describe topographic maps and geologic maps at the end of the chapter. So we will use profile views when we study cross-sections or models of the inner structure of Earth. So when we're looking at the inside of the Earth and we're looking at the core and the mantle from the inside, we will be using plan view, okay? So map legends and scales. So map have two features to help you read and understand the map. One feature is a series of symbols called a map legend. That's up here, okay? This is a legend. The other is a ratio which establishes math scale. So here's a picture of what scale will look like, okay? So map legends use specific symbols to represent certain features on Earth's surface, such as roads in a city or restrooms in a park. These symbols allow map makers to fit many details on a map without making it too cluttered. All maps include a map legend, which is a key that lists all the symbols on the map so that you can see what the symbols mean. It also explains what each symbol means. For example, if the map legend has a dashed line, see here, see this big dashed line that goes all the way around, we can look over here at our legend and it says that that is a trail. Okay? So map scales are used when map makers draw a map to show how big or small to make the map. They need to decide on the scale. So the scale is the relationship between a distance on the map and the actual distance on the ground. So the scale can be verbally written, such as like 1 centimeter is equal to 1 kilometer. The scale can also be written as a ratio, such as 1 to 100, because in this ratio there are no units. So verbally you would say every unit on the map is equal to 100 units on the ground. If your unit were 1 centimeter on the map, it would be equal to 100 centimeters on the ground. If you drew a map of your school at a scale of 1 to 1, your map would be as large as your school. So figure 3 gives you a written scale, a ratio scale, and a graphic scale in the map legend. Okay, so that's over here. And each one can be useful in different ways. For example, the graphic scale, or the scale bar, which is right here, would be used in measuring distances on the map. You would have to measure it to find out that 1 centimeter is equal to 1 kilometer. Okay? So figure 4, which is right here, shows another way in which scales are useful. Models are built with scaled measurements that can be increased or decreased relative to the measurements of real objects. Models have the same relative proportions as the object they represent, similar to a map scale. So if you see this, this is a model of a city, right? And she is taking steps to see if the scale is proper, okay? To find your way to a specific place, you need a way to determine where you are on Earth. Imagine telling someone your exact position on the snow-covered continent of Antarctica. It would be difficult to describe. Ship captains and airplane pilots experience the same problem as they plot their courses across the oceans or above the cloud-covered Earth. So this is where longitude and latitude, oh my goodness, I can't speak today either, longitude and latitude come into play. Please do not stress about it too much. I promise you this is going to be very understandable for you guys, okay? So, have you ever played a game of chess or checkers? If you have, you know the board is set up with grid lines to help you choose your moves and the position of the pieces on the board. Well, long ago, map makers created a system for identifying locations on Earth that uses a similar grid system. So this system uses two sets of imaginary lines that encircle the Earth. These two sets of lines are called latitude and longitude. The intersection of a line of latitude and a line of longitude can pinpoint a location on a map or globe. So for longitude, map makers started the grid system with a line that circled Earth and passed through the North Pole and the South Pole. The half of the circle from the North Pole to the South Pole passes through Greenwich, England, and is known as the prime meridian. The prime meridian is shown in figure 5. So here we go, over here to figure 5, and here, right here, this line is the prime meridian, okay? The other half of the circle is the 180-degree meridian. Similar circles are drawn at every degree east and west of the prime meridian. So longitude is the distance in degrees east or west of the prime meridian. The prime meridian and the 180-degree meridian combine to divide Earth into east and west halves or hemispheres, the eastern hemisphere and the western hemisphere. East of the prime meridian, longitude is measured in degrees east, and west of the prime meridian, longitude is measured in degrees west. They both meet at the 180-degree meridian. All the meridians pass through the North Pole and the South Pole. So for longitude, okay, we're going to go long. Think long, up and down, right? And you're going to go, see all these lines, the red ones and the blue ones on this side? Those are all longitude lines, okay? And they all have different degrees, okay? Don't panic, I promise. We'll be okay. So latitude, map makers also drew lines east to west around the Earth, and these lines are called latitude. And they're perpendicular to the lines of longitude. So longitude goes up and down, and latitude goes left to right, okay? The center line is called the equator, which is this black line right here, and it divides the Earth into northern hemisphere and southern hemisphere, okay? Latitude is the distance in degrees north or south of the equator. So unlike the lines of longitude, lines of latitude are parallel, okay? The equator is the largest circle. All the other circles become smaller and smaller as they come closer to the poles, okay? So how can you use this grid system to plot locations. Well, first, think about why longitude and latitude are measured in degrees. So Earth is a sphere, right, which is a ball, which is a circle. So if you look straight down, it looks like a circle, right? So like a circle, a sphere is divided into 360 degrees. If we remember from math, 360 degrees makes a perfect circle. So if we look at figure 5, which is over here, the latitude at the equator is 0. So here we go. This is the equator, and see, this is 0 degrees, right? And all the other lines of latitude are measured in degrees north and south. The North Pole is 90 degrees, and the South Pole is 90 degrees, okay? So lines of longitude are measured in degrees east or west of the prime meridian. Remember, they go left to right. Well, they go up and down, but left is western, right is eastern. And these are 180 degrees, okay? So if you look here, the prime meridian is 180 degrees, okay? So any location on Earth can be described by the intersection of the closest line of latitude and the closest line of longitude. Latitude is always stated first, okay? So you always start with the equator measurement first and then the prime meridian, okay? So because longitude and latitude lines are far apart and excuse me, and help determine locations, we divide each degree into 60 minutes and each minute into 60 seconds, okay? So if you look here on this globe, it says use the diagram on the right to answer the following questions. So which city is located at 20 degrees north and 155 degrees west? So I'm not going to make you guys do this, but I just want you to understand if you're going to try to figure out what the answer is, you're going to start at the equator line, right? Because latitude lines are measured first. So you would go 20 degrees. So you would go 20 degrees north. So you're going to go up to here, 20 degrees north, okay? And then 155 degrees west, okay? So you're going to go here. Okay, does that make sense, guys? Like I said, it's going to be easier than you think, I promise. So, the last thing, all right, guys, sorry about that. My dogs are crazy. So, the last thing that we can determine when we're using maps are time zones. So, when it's high noon at your location, the sun is directly overhead, but as Earth rotates, the sun is directly above different locations at different times. So businesses in cities many miles apart will have a hard time doing business with each other if every city had its own time. So time zones were created to make travel, communicating, and doing business easier for everyone. So a time zone is the area on Earth's surface between two meridians where people use the same time. So the reference or starting point for time zones is the prime meridian. Earth is divided into 24 different time zones, and the width of a time zone is 15 degrees longitude. But, as shown in figure 6, which is down here, the time zones don't follow the meridians exactly, okay? So their locations are sometimes altered at political boundaries. So notice how the time changes by 1 hour at the boundary of each time zone. What happens when you go halfway around the globe? Well, why do we need a starting point for time zones? Well, if we didn't have a starting point, who would know where the time began, right? So the line of longitude 180 degrees east or west of the prime meridian is called the international dateline. So there are 24 time zones and 24 hours in a day, right? So because one location can't have two different times on the same day, the day changes as you cross the date line. So if you come from east to west, it is the day before in the west. And if you cross from west to east, it's the next day. So if you notice that the international dateline does not follow the 180 degrees exactly. So the international dateline, it's kind of hard to see on here, but it's this red line. So if you look, you would think a time zone should go like straight down, right? No, this one goes like over this way, and then it cuts back over this way, and then cuts down again, okay? So this is because some of the island nations would be divided by the line. So it would be one day on one island and a different day for another island in the same nation. So to avoid this, the international dateline actually goes around them. So I used to live in Florida, and I lived at a base called Eglin, and there my time was 1 hour behind my parents, who also live in Florida, but they live in Tampa. So even though we were in the same state, we were in different time zones. Pretty silly, huh? So last thing are map projections. So since a globe is spherical, like the Earth, Earth's features are not distorted on the globe. Maps, however, are flat. So how can a flat map be made from a sphere? Well, one way to transfer features from a globe to a map is to make a projection. So cylindrical projections are pretty cool. Imagine a light at the center of a globe, okay? So put a flashlight right in the center. It would throw those shadows of the continents and the latitude and longitude lines onto a sheet of paper, right? If it were wrapped around the globe. Well, because the paper is shaped like a cylinder, we're going to look at figure 7, this one here, okay? This is called a cylindrical projection. So it results in a map that represents shapes near the equator very well, but the ones that are by the poles are enlarged because, remember, wherever you're shining a light, the shadow directly in front of it will be true to size, but then it'll spread out as you get further away, right? So notice that in the cylindrical projection, Greenland appears to be larger than South America, but we all know that Greenland is about 1/8 the size of South America. So if you look up here, we've got Greenland, okay? So conical projections is like wrapping a cone around the globe to make this projection, okay? And it has a little bit of distortion near the line of latitude where the cone touches the globe, okay? But it is distorted elsewhere. So all types of projections, unfortunately, distort the shapes observed on a sphere because there's no way to perfectly put a projection onto a flat piece of paper from something that is round, right? So in other projections, the continents are represented accurately only because the other areas, such as the oceans, are distorted, right? So either way, any of these projections are going to be, distorted and not true to size. Your best bet for trying to map the Earth is to use a globe because the Earth is round and a globe is round. Okay, so that's it for today. We'll get a little bit deeper into it next week. Have a good weekend.